All right, welcome everybody. So in this video, I want to define what a subspace of a vector space is and then verify with one example down below whether or not this example is a subspace or not. And then similar to how we treated vector spaces, we can go through a number of examples to check and see whether they satisfy the properties for a subspace or not. So for a subspace here, we first consider that we have some vector space V. So this set of objects V also has an addition operation defined on it between vectors, and we also have a multiplication by a scalar operation defined. So when we say vector space V, that's also implied that we have an addition operation and a scalar multiplication operation. And now I'm going to take some subset of objects from V that will denote H. And so a subset of V is called a subspace as long as there are three properties that are satisfied. So this is nice, right? With vector spaces, we had 10 properties to check. Now we just have three. So the first is we want to make sure that the zero vector that we know exists in vector space V, it is included in H. So H must include the zero vector. That's the first condition. Secondly, we want to make sure that if I take any two vectors in this subset H and I add them together using the way that addition was described in vector space V, that the result of the sum U plus V is also going to be in H. So this is what we would say this is closed under vector addition. Taking the sum of any two vectors in H gives us a vector in H. And similarly, we want to have multiplication by scalars closed. So given any vector u in H, then for any scalar c, the product c times u is also going to be in H. So we just want to make sure that for the operations that we defined on V, these operations are closed when we apply them to objects in H. And we also want to make sure that the zero vector is definitely included in our subset H. So let's take a look at this example. V is R3, where we have the usual vector addition and scalar multiplication. So we know this is a vector space. Now let me consider the subset of vectors H given by the first entry. It could be anything. The second entry has to be 0. And then the third entry could be some real number. So we're going to consider vectors of the form A, 0, B. So these are vectors in R3. And we want to check to see whether this is a subspace of R3. So the first condition is the zero vector in H? And yeah, if we set A equals 0, we set B equals 0, then we get the vector 0, 0, 0, which is a in H, so this is great. So the zero vector is in subset H, so that part is satisfied. Secondly, we would want to check that if I take any two vectors in H, so maybe one of them is A0B, and then I add to that some other vector, we'll call this C0D, that the result, and here we're using regular matrix addition, so we add, vector addition. So we add our vectors component-wise, and I wind up with a vector that has 0 as the second entry. So this is certainly closed under addition. Since I add any two vectors that have 0 as the second coordinate, we're going to get a vector that has 0 as the second entry. And the same goes for scalar multiplication. So if I multiply vector A0B by the scalar k, then using our regular scalar multiplication, we would multiply k by each entry, and the resulting vector is going to have 0 in the second position. So this is going to be in H. And I'm using this symbol over here to denote included inside of a set. So this means this vector is in the set H. So there we go. That was a lot quicker to check than the 10 conditions that we had to check for a vector space. Just want to make sure the 0 vector is in here. Yup. When I add 2 vectors in H, I get a vector back in H. Yup. And when I multiply anything in H by any scalar K, the resulting vector that we get is in H. And yup, that was true over here. So here is an example of H is an example of a subspace of the vector space R3.